All right, guys, we're picking up from where we left off with work done by multiple forces. So let's say that there's not just one force that acts on a particle. So on the last slide, I see that I can integrate the work based on integrating force and with respect to a certain amount of displacement. So with respect to x. And that's just if I'm thinking about one varying force. In most cases, you're going to have multiple forces that are acting on a system. So if I have that, I can't just model only one force. I have to think then about the total work being done on the system, which is then going to be done by net force. So in the last chapter, we thought that we got away with writing the sum of the forces in the x direction, the sum of the forces in the y directions, but we did not get away from them because they are right here. So to find work, I'm going to find the sum of the forces in the x and integrate that with respect to x. Okay, and this is the exact same thing. The only difference between these two is that in this I'm showing it's just x in the horizontal direction, and r down here I'm just showing that it's overall displacement. Okay, that equation is what I am going to model if I'm talking about a non-deformable system. I can model it as a particle. If I have a deformable system, then I can't model it as a particle. So that's just going to be equal to the algebraic sum of the scalar product here. You will probably never, ever have to use this one. AP test will always have non-deformable objects. So we're going to be focusing on this one, not so much this one. Okay, if I give you this, I say a force acting on a particle varies with x as shown. Calculate the work done by the force on the particle as it moves from x equals 0 to x equals 6 meters. Because these forces are just nice straight lines, I don't have to worry about integrating here at all. All I have to do is do a little geometry, because I can find the work based on all of the work is going to be equivalent to that shaded region here under those lines. So I could find the area between 0 and 4 and 0 and 5 here. Find that area by just thinking about the area of a triangle. So I could take length times width, find that number. So what would that be, 20 joules? Then I can find the area underneath this triangle here. So that's going to be 1/2 base times height. So I would do 1/2 2 times 5. And then that would give me 5 joules. So then ultimately my work done would be the area of this one with the area of this one. So my work should be 25 joules. This is going to be the type of multiple choice question that you're going to see about finding the net work that's done. You'll see that on the y-axis, if it's force, on the x-axis, it'll be displacement. I can always find work then just by finding the area underneath that curve. Now, if there was a curve, if force was varied, I would have to integrate it. But there's no way that you can do that on a multiple choice test just with numbers. There's just no way. Okay, on work done by a spring, so we're about to get into Hooke's law. If we look at part A, let's go to part B. We'll initially start here. At part B, I have a spring that's attached to some mass, and right now it's at rest. So I call this the spring force. Because x is 0, this is just going to be the natural length of the spring. So the spring force is going to be equal to 0. X is at some type of resting point. If I stretch out the spring, out like I see here in A, the spring is moved away in the positive x direction, away from the equilibrium point. So in B, x is equal to 0. It's at its equilibrium place. At A, I stretch out the mass. The spring is now stretched. Which direction does the mass want to go? Which direction would I call the spring force? It's going to be moving back toward its equilibrium position. So when x is positive, I see that the spring force is going to be in the opposite direction. It's trying to pull it back towards its equilibrium position. We will call this the restoring force. So this force, the spring force, is also called the restoring force. It doesn't want to be out of its equilibrium position. So I stretch it out, x is positive, spring force is going to be in the opposite direction. Let's say I don't stretch it out, let's say like I have here in C, let's say that I compress it. X is now negative. So if x is negative, x would prefer to be in its equilibrium position at 0. That means that the spring force is going to be toward the right. It's going to be moving in the positive direction. So displacement and spring force are always going to be opposite in sign, okay? And that's because we always want the spring, we always want that mass to be back at x equals 0. We always want it to be in its equilibrium position, okay? This spring force can be calculated by taking f of s is equal to a negative kx. This is called Hooke's law. K is a constant. We call that the spring constant. And ultimately, that spring constant is just a measure of how stiff the spring is going to be. That's going to be measured in a Newton per meter. X is just the displacement that mass that's attached to the spring is moving. So I'm always going to assume maybe it starts at 0, and if it's stretched, it's going to be positive. If I compress it, it's going to be negative. Okay, but we're always assuming it with respect to its equilibrium position. So springs, the spring force, or Hooke's law, F of S is equal to a negative kx. And let's think about this. If I compress the spring, then that means that x is going to be negative. So if f of s is equal to a negative kx and x is negative, spring force would be positive. And that makes sense because the spring force is trying to push the mass back towards its equilibrium position because they should be opposites. So that negative sign there is trying to help indicate the position of the spring force with respect to the position of the displacement. Okay, so when x is positive, spring is stretched, F will be negative. When x is 0, F is 0. Spring force, I don't have one. I don't have a restoring force. And when x is negative, the spring is going to be compressed, so F is going to be positive. Okay, if we have a very small value of K, then that means that the spring is going to be really, really soft. If if my spring constant is a really large number, then that means that spring is going to be very, very stiff, okay? If we think about the work being done by a spring, then I can think about work if I know that work is equal to force times displacement. So I'd rather just derive this than you looking at this right now. I think it'll just be easier to derive it. Okay, if I want to find the work done by a spring onto some mass. Okay, I know that work is equal to force times a displacement. Or maybe we prefer that to just be x. Okay, if this is for a spring, and I don't know also because that force is going to vary as it starts to oscillate back and forth until it gets to its equilibrium position. So that means that I need to think about this as an integral. So force is going to be integrated with respect to x, okay? So in this case, I know that the spring force, because we just saw spring force is equal to a negative kx. So let me sub that in here for the spring force. So work is equal to negative kx dx. How do I do an integral? I don't know that you know that yet from calculus. So if I want to do an integral, it's really just doing the opposite of a derivative. And this is probably the one that we're going to have to know the most. So if I integrate x to the nth, and that would be with respect to dx, then what we're going to do is, it's going to be equivalent to x with n plus 1 over n plus 1. So what does that mean? Right now I just want to think about negative kx. I'm not going to integrate a negative, so actually let's just take that negative out. I want to try to integrate kx. It's going to be the opposite of a derivative. So k is just a constant, so I'm really just integrating x. If I integrate x, I'm going to follow this. X n plus 1. Well, its exponent is 1, so 1 plus 1 is going to give me x squared, but then that's going to be over n plus 1. So really this is 1/2 x squared. And then if I took the derivative of that, then it would be 2 times that 1/2, which would then just leave me with x. So an integral is really just the opposite of a derivative, okay? And that form is going to be this. If I want to integrate x to the n, then it's going to be x n plus 1, x to the n plus 1 over n plus 1. So just x would be 1/2 x squared. So that would be the integral of it. Okay, so let me erase this really quick. We'll go back to doing this. Okay, I'm thinking about this integral happening over a range that's happening from the initial position to the final position. That's how I'm integrating it. So this is going to be k 1/2 kx squared, and I just integrated this based on what we just did. So I'm starting off with 1/2 kx squared initially, and then I'm going to think about that also with the final then. So then that's going to be 1/2, because I have the negative, 1/2 kx final squared. So I'm integrating both pieces of this. I got this just by integrating x, and k's in here because it's a constant. I needed to include that in here. Then I also did the same thing to the final. So if I want to find the work done by a spring, then it's going to be this equation here. Okay, I don't think that this is anything that I've ever seen that you necessarily had to derive, but I do want us to know how to derive it. So we're always starting with, I know that work is equal to force times that displacement, but if that force is varying, I'm taking the integral of force with respect to x. Since I know that the spring force is equal to kx, I subbed that in for the spring force, and then all I did was integrate x. When I integrate just x, I get 1/2 x squared. But then I want to think about that in terms of that range of the initial x position to the final x position. So I did that by showing that this is what I'm starting off with initially, and then this is the amount of work that I've done finally. So this is how I would find work done by a spring. Okay, which is showing us that right there as well. So I can find it over in an entire range, or I could maybe just find it by doing work is equal to 1/2 kx squared, and that's just maximum. So maximum meaning that if I'm starting off at 0 and then stretching it, then ultimately if x is going to be 0, it totally cancels out one of those things. So all I really need if I'm starting at 0 is one of those pieces. If you're not starting at 0, then that's where we're going to use that very last equation that we just derived, which is what we have here. So we already derived this, 1/2 kx initially squared minus 1/2 kx final squared. Okay, suppose an external agent applied force stretches the spring. The applied force is going to be equal and opposite to the spring force. So let's say that I compress this spring, it should be equal and opposite to the spring pushing back on that applied force. Okay, so there's just Newton's third law coming into play. Let's try to do a problem with this. So it says a common technique used to measure the force constant of a spring is demonstrated by the setup in the figure to the right. So ultimately I have a spring, it doesn't have a mass attached to it. I attach a known mass to the spring, and then I see that it has moved some type of displacement. So the elongation is caused by the weight of that attached object. So I know weight, I know the mass of that particular object, I'm able to find K. That's my goal in this first part. If a spring is stretched 2 centimeters by a suspended object having a mass of 0.55 kilograms, what is the force constant of the spring? Let's go back to do a free body diagram, because Lillian loves them. Okay, so we had our spring, it was attached to a mass, there was the displacement. Displacement was 2 centimeters, so let's just go ahead and call that 0.02 meters. And then the mass of that was 0.55 kilograms. What is K? Okay, so free body diagram tells me that I have the spring force, acting up, weight force acting down. So here's mg, here's the spring force. If that mass is now at rest, it has stretched the spring, the mass is just sitting there, these two then have to be equal. So F of S minus mg equals 0, because that would be the sum of the forces in the y. So that means F of S equals mg. I also know that the spring force is equal to a negative kx. So negative kx equals mg. I know x, I know mass, I know acceleration due to gravity, so I can find now k. So k should equal mg over x. So if we do that, we should get k to be 270. So just plug in your numbers. K should be 270 Newton per meter. It's a Newton per meter. And if we think about that, that should make sense. K is equal to, spring force is equal to K times X. We know that forces should be measured in newtons. I know X is measured in meters. So I need to get rid of a meter somehow. So a Newton per meter will do just that. So that's why K is going to be measured in Newton per meter. So we found K to be 270 Newton per meter. Let's do part B. On part B, it says how much work is done by the spring on the object, should say how much work is done by the spring on the object as it stretches through this displacement. So I started off at something initially, I end at something finally, so we're going to use that same equation that we just derived a minute ago with work is equal to 1/2 kx initial squared minus 1/2 kx final squared. Okay? So work is equal to, we just found our spring constant, and initially this was at 0, it was at rest, and then I stretched it. So initially this whole thing is 0. Do I even need to write that? Lillian, do I need to write that?
Mrs. Warren, you'd be a fool.
I'd be a fool to write that. So that's 0. So minus 1/2 k, we just found that, that's 270 Newton per meter, and then its final position was 0.02 meters, but I want to square that. Okay, so work is equal then to a negative 5.4 times 10 to the negative second joules. Okay, why does it make sense that it is negative? It makes sense that it is negative because the displacement, actually, you tell me why this makes sense. So you had one question that you had to find for me for scalar product. I want you to tell me and write down an explanation so you can write that on the whiteboard as to why it makes sense that the work is negative. So make sure that you add that into your phenomenal explanation for me on Monday. Okay, one last thing. I want to just introduce kinetic energy because we did it in AP Chem. We're doing it again here, except this part you're probably not going to like as much. Kinetic energy, we already know, is 1/2 mv squared. So another possible result that work can influence a system is that it can change its speed. It can make that object move. We know that systems can possess kinetic energy because they have potential energy, and that potential energy can be changed and transferred into kinetic energy. So kinetic energy is 1/2 mv squared. We know K is kinetic energy, it's measured in joules. We know mass here has to be measured in kilograms. Speed of that particle is v, that has to be in meters per second. We also have this phenomenal thing called the kinetic work energy theorem. But I'll wait until Monday so you can be in suspense for it all weekend long. I will see you on Monday. Bye.